Prolog, short for Programming in Logic, is a fascinating computer programming language. It's not like other languages you might know. Prolog is all about logic. It's about declaring facts and rules, then you ask questions. Prolog uses its logic to find answers. Prolog is special because it's good at representing knowledge. This makes it perfect for artificial intelligence, or AI. In AI, we want computers to think like us. Prolog helps us do this. It lets us teach computers about relationships like family trees. We can also teach them rules like the rules of a game. One area where Prolog shines is natural language processing, or NLP. NLP is how computers understand human language. Prolog's logic makes it easy to analyze sentences. It can understand the relationships between words. This helps computers understand what we mean. Prolog is a declarative language. This means we tell it what we want, not how to get it. In other languages, we write instructions step by step. In Prolog, we declare facts and rules. Prolog figures out the rest. This makes Prolog perfect for tasks where logic is key, like AI and NLP. Prolog stands out for its unique features. It's a declarative programming language. This means you focus on the what rather than the how. You tell Prolog facts and rules about your problem. You don't tell it how to solve the problem, step by step. Prolog uses facts and rules to represent knowledge. Facts are basic statements that are true. For example, Socrates is a man. Rules are logical relationships between facts. For example, if X is a man, then X is mortal. Queries are how you ask Prolog questions. You use the facts and rules to find answers. Prolog's engine searches its knowledge base. It uses a process called unification to find matches and deduce answers. Unification is a core mechanism in Prolog. It's how Prolog finds matches between terms. Terms can be constants, variables, or structures. Unification allows Prolog to perform logical deductions. This is how it answers your queries. Prolog has a rich history, dating back to the early 1970s. Its roots lie in the field of logic programming. Logic programming aims to use logic as a means of computation. The birth of Prolog is attributed to Alain Colmerauer and his team in Marseille, France in 1972. They developed Prolog as a tool for natural language processing. The language quickly gained popularity in Europe and Japan. It was used in various AI research projects. One significant milestone in Prolog's history was the development of the Warren Abstract Machine, or WAM, in the 1980s. The WAM is an efficient virtual machine designed specifically for Prolog. It greatly improved the performance of Prolog implementations. Over the years, Prolog has evolved with the addition of new features and libraries. It has been used in a wide range of applications. These include expert systems, natural language processing, and theorem proving. Today, Prolog continues to be an important language in AI and logic programming research. If you're interested in exploring the world of logic programming, setting up Prolog is surprisingly easy. One popular and widely used Prolog implementation is SWI Prolog. It's free, open source, and available for various operating systems. To get started, head over to the official SWI Prolog website, download the appropriate installer for your operating system, follow the on-screen instructions to install SWI Prolog on your computer. The installation process is generally straightforward. Once SWI Prolog is installed, you can launch the SWI Prolog interpreter. You'll be greeted with a prompt where you can start typing Prolog code. The interpreter allows you to interact with Prolog directly. You can define facts, rules, and pose queries. SWI Prolog also comes with a built-in editor called PCMax. PCMax provides a convenient environment for writing and editing Prolog programs. You can find PCMax in the SWI Prolog installation directory. It offers syntax highlighting and other helpful features for Prolog development. Section 5. Building blocks of Prolog facts, rules, and queries. In Prolog, the fundamental building blocks of knowledge representation are facts, rules, and queries. These elements form the basis of Prolog's logical reasoning capabilities. Facts are simple statements that assert something is true. They are expressed as predicates followed by arguments enclosed in parentheses. For example, the fact Socrates is a man can be represented in Prolog as. Rules are used to define relationships between facts. They consist of a head and a body separated by the symbol. The head specifies a condition that is true if the body is true. For example, the rule all men are mortal can be expressed as. Queries are questions posed to the Prolog system. They ask whether a certain goal is true based on the defined facts and rules. Queries are also expressed as predicates with arguments. For example, to ask Prolog if Socrates is mortal, we would use the query. Section 6, Prolog, syntax, atoms, numbers, variables, and complex terms. Let's dive into the world of Prolog syntax. Understanding the basic building blocks of Prolog code is essential for writing meaningful programs. Atoms are the simplest elements in Prolog. They are used to represent specific objects or constants. An atom starts with a lowercase letter or is enclosed in single quotes. Examples of atoms include and. Numbers are another fundamental data type in Prolog. They can be integers or floating point numbers. Integers are whole numbers or floating point numbers have decimal points such as or. Variables are denoted by uppercase letters or underscores. They act as placeholders for values that can change during program execution, for example, and are all valid variable names in Prolog. Complex terms are formed by combining atoms, numbers, and variables using functors. A functor is an atom that precedes a list of arguments enclosed in parentheses. Complex terms represent structured data. For example, represents the fact that John is the father of Mary. Section 7. Constructing knowledge bases. Representing information with Prolog. Prolog excels at representing knowledge in a structured and logical manner. By defining facts and rules, you can create knowledge bases that capture relationships and constraints within a specific domain. Let's say we want to create a simple knowledge base about family relationships. We can start by defining facts about individuals and their relationships. For example, parent John Mary, parent John Peter, parent Mary Susan. These facts state that John is a parent of Mary, John is a parent of Peter, and Mary is a parent of Susan. Next, we can define rules to infer other relationships based on the defined facts. For example, grandparent X, Z, parent X, Y, parent Y, Z, sibling X, Y, parent Z, X, parent Z, Y, X, =Y. The first rule states that X is a grandparent of Z if X is a parent of Y and Y is a parent of Z. The second rule defines siblings as individuals who share the same parent but are not the same person. Section 8. Prolog's logical prowess, conjunction, disjunction, and more. Prolog's logical power lies in its ability to handle complex logical operations. It supports conjunction, disjunction, negation, and other logical connectives. This allows you to express intricate relationships and constraints. Conjunction, represented by the comma, allows you to combine multiple goals. All goals in a conjunction must be true for the entire conjunction to be true. For example, the query will succeed only if John has a male child. Disjunction, represented by the semicolon, allows you to express alternative goals. At least one of the goals in a disjunction must be true for the entire disjunction to be true. For example, the query will succeed if either John or Mary has a child named X. Negation, represented by the operator, allows you to check if a goal is not provable. For example, the query will succeed if there is no individual X for whom John is a parent. Section 9. Variables and unification, the power of Prolog's inference engine. At the heart of Prolog's inference engine lies the concept of unification. Unification is the process of matching terms together to see if they can be made equivalent. This process is what gives Prolog its power to perform logical deductions. Variables play a crucial role in unification. A variable can be instantiated to any term, including other variables. When Prolog tries to unify two terms, it attempts to find values for the variables that make the terms identical. For example, consider the query. This query asks Prolog to find all values for which the term is true. Prolog will search its database of facts and rules and try to unify the query with any matching terms. If Prolog finds the fact, it can unify the variable with the atom. This means that the query is true when is equal to. Unification is a powerful mechanism that allows Prolog to answer complex queries by finding values for variables that satisfy the given conditions. Section 10. Prolog in action, exercises to test your knowledge. Now that you've learned the basics of Prolog, it's time to put your knowledge to the test with some hands-on exercises. Exercise 1. Defining facts. Define the following facts in Prolog. John likes apples. Mary likes bananas. Apples are red, bananas are yellow. Exercise 2. Writing rules. Write a rule in Prolog that defines a person as fruit. Underscore lover if they like both apples and bananas. Exercise 3. Creating queries. Write Prolog queries to answer the following questions. Who likes apples? What is the color of bananas? Is there anyone who is a fruit lover? Exercise 4. Implementing a family tree. Create a Prolog program that represents a family tree with facts for parents and rules to infer relationships like grandparents, siblings, and cousins. These exercises will help you solidify your understanding of Prolog's syntax, knowledge representation capabilities, and logical reasoning.